Here are solutions to homework set number 1 for ECE 376. For this homework set, we're just looking at some background on the PIC processor, what it's capable of. Well, the first problem is actually more for Bison Academy. So Bison Academy is the semi-official website for the ECE department and NDSU. If you go to 376, you've got the class page. Go under homework sets and solution. You've got homework sets and solutions for the past 5 semesters. If you look at homework set number 9, something we're going to get to a little bit later, the first problem was measure how long it takes to drive the LCD display. So here I can sit there and see how it was called, the different routines. The answer we're looking for is right here, 6.2 milliseconds. For the other problems, let's go down here. If I want to drive a load, the PIC can only drive 25 milliamps. What that means, hold on a sec, is that the resistor R3 has to be at least 200 ohms. What that means is if you want to drive an 8 ohm speaker, you really shouldn't. It won't hurt the PIC, but it violates the max current. 5 volts at 8 ohms is 600 milliamps. PIC can't do 600 milliamps. What you need to do is add a 200 ohm resistor in series with the speaker, or have a load with the impedance of more than 200 ohms. Then the PIC can drive it directly. Problem 3 says if I have a voltage divider like this, if R2 is 2000 ohms, what's the voltage at V1, and what's the resolution? What's the change in resistance that I can see? Well, at 2000 ohms, the voltage is by voltage division, R2 over R1 plus R2, 1.887 volts. The PIC can read analog voltages. The resolution is 4.88 millivolts. It basically converts a voltage to an integer, 0 to 1023. The smallest change you can see is 1 count. 1 count corresponds to 4.88 millivolts, which means that the voltage has to change by 4.88 millivolts, go up to 1.8916 volts. Well, the resistance that causes that much change is 2008 ohms for a difference of 8.32 ohms. So that's the resolution on a PIC. I can measure a 2000 ohm resistor with a resolution of 8 ohms using a voltage division. If I change that resistor to a temperature sensor, in your lab kit there's a thermistor. This is the relationship between resistance and temperature, where T is temperature in degrees C. As temperature changes, resistance changes. If I can measure the resistance, I can measure the temperature. At 2000 ohms, the corresponding temperature is 10.02 degrees Celsius. So if I measure whatever the voltage was, 1.887 volts, I know that R is 2000, I know the temperature is 10 degrees. I've got a temperature sensor. And that's kind of how the digital temperature sensors work, like in your thermostat. The smallest change I can see is 8 ohms. That corresponds to a temperature 9.94. Taking the difference is 0.08 degrees Celsius. What that means is the PIC can measure temperature with a resolution of 0.08 degrees Celsius. So that's in terms of the analog input. The PIC can also measure time to 1 clock, which is 100 nanoseconds. So to give an idea of how small 100 nanoseconds is, we've got problems 5 through 9. An average NFL quarterback can throw a football 87 kilometers an hour. In 100 nanoseconds, that football travels 2.4 microns. To give an idea how small that is, a human hair is about 180 microns. A bacteria is about 1 micron. So you can almost see the football traveling bacteria by bacteria. That's really, really small. Problem 6 goes to a 555 timer. If I can convert something to frequency, or to time, I can measure time really, really accurately with a microprocessor, 100 nanoseconds in this case. So if I build this 555 timer with R1 being 1K, R2 being 2K, 6.1 microfarad, the period is 346 microseconds, the frequency is 2885 Hertz. If I make R2 a variable resistor, I can measure resistance. I've converted resistance to frequency. I can measure time or frequency really, really accurately. So if time increases by 100 nanoseconds, the smallest time change I can detect with a pick, the frequency becomes 2884 Hz, or a difference in frequency 0.8. So with a pick I can measure 2885 Hz with a resolution of 0.8 Hz. If I make R2 a variable resistor, then the period, this is the period of a 555 timer, for that to increase by 100 nanoseconds, R2 has to increase by 2000.72 ohms, or a difference of 0.72 ohms. What that means is if I use this as an ohm meter, I can measure 2000 ohms with a resolution of 0.7 ohms. If I replace R2 with a thermistor, then 2000.72 ohms corresponds to 10.028 degrees Celsius. A difference, well, here's 2000 ohms, here's 2000.7 ohms. The difference is 0.007. So that's my resolution temperature. If I convert temperature to frequency, I can measure the temperature to 0.007 degrees Celsius. So that's homework set number 1. Just kind of a little bit of background. The processor we're using in this class isn't the world's most powerful processor, but it's still pretty darn impressive. With it, I can measure temperature, resistance within 8 ohms, 0.08 degrees Celsius, using the analog input. If I do a trick and convert it to frequency and measure time to 100 nanoseconds, something we'll do later in this semester, I can measure how far a football's thrown with a resolution of 2.4 microns. I can measure frequency with a resolution of 0.8 Hertz, or temperature to 0.007 degrees Celsius. That's homework set number 1 for ECE 376.